Алекс, добро пожаловать и расскажите, пожалуйста, немного о том, что такое dark matter, насколько это может быть применимо, насколько законы физики применимы в реальной жизни и куда нам двигаться дальше. Спасибо.
Спасибо большое за приглашение. Я почти уже потерял свой голос, так что простите, пожалуйста. Я рад, что я еще говорю, но вот сегодня утром было так, я не знаю. Так что мне очень приятно тут быть сегодня с вами. Я русского происхождения, Филиппенко, конечно, украинская, но я родился в Америке и жил там всю свою жизнь, и уже много лет не говорил по-русски, так что я каждый год все больше и больше забываю. И я разговариваю с сильным американским акцентом. Простите, пожалуйста. И мне много легче говорить по-английски, особенно когда технический словарь мой не очень хороший. Так что эта лекция будет по-английски, простите, но так мне легче. И я не знаю, есть ли тут переводчик. Окей. Спасибо. Очень приятно тут быть. Так что вот я хотел начать эту лекцию с этим вопросом. Well, actually, this is where I switched to English, right? Yeah. So it's obvious to most people what the value is of physics and applied science and engineering. You know, it's the type of thing that improves lives, produces technology, is good for the economy. We see here a steam turbine, the beginning of the Industrial Revolution. More recently, of course, there are pacemakers that help keep us alive, and all the various little things that we now have. But it is a reasonable question to ask, why spend national funds or corporate funds on pure curiosity-driven research? Should we invest in this kind of research when it has no obvious practical application? Why should we do astronomy and theoretical physics? So I have three replies. The first is simply that, I guess this didn't advance, but you can read it. It's just what I said right now. The first is that of all known animals, we are the only ones who have the curiosity to ask these kinds of questions including those of our very origins, and the intellectual capacity to try to answer them, and the hands with an opposable thumb with which to build machines that can help us answer such questions. So dolphins and whales are obviously quite intelligent, but there's no evidence whatsoever that they're capable of abstract thought and the possibility of answering such questions. The second reason is that studies of this sort get kids excited into fields of science and technology. They won't necessarily become astrophysicists. That's okay. One doesn't need too many of us in the world at a given time. But these children are more likely to move on in applied physics, medical physics, computer science, technology, engineering, and astronomy is the bug that bites them. I'm on the board of directors of a center in Oakland, the Chabot Space and Science Center, and we see these kids get so excited by the kinds of things that they learn of an astronomical nature. There we go, oops. We can show them objects on Friday and Saturday evenings through the telescope, and we see the look of awe and wonder that they have when they see a cloud of gas like this, the Orion Nebula, from which new stars are forming right in front of our very eyes. Our own solar system and the many planets formed 4,500 million years ago from such a cloud. And we can also look at galaxies like our Milky Way Galaxy. This is a different galaxy, but it's a collection of 100,000 million stars gravitationally bound together. And the realization that our sun is only one among so many stars in a galaxy like this is just mind-blowing to children. I know that when I was young, the lunar landings were a great inspiration. And although I had already decided to become a scientist, this provided additional incentive. And I saw many friends of mine become interested in science for the first time because of this great achievement, the lunar landings. So there's no doubt that astronomy gets kids excited in the STEM fields: science, technology, engineering, mathematics. So for that reason, it's important as well. And then the third reason are the unanticipated applications. And as one example, I just give you quantum physics. A century ago, when Einstein, Planck, Bohr, Schrödinger, and others were developing quantum physics, they had not the slightest practical application in mind. They were driven by a desire to understand nature, in particular, the nature of light. What is light? And the existence of atoms. According to classical physics, in fact, atoms could not exist. And there were many other questions as well, but those were two of the main questions. Fast forward 1 century, and you cannot imagine today's world without an understanding of the microphysics, of the physics on very small scales. And let me give you just as one example, lasers. Lasers are an entirely quantum phenomenon. The light is coherent. It's all in phase. And here are applications of just laser physics. And all of us, of course, have our devices, these things. You know, they're based on the fact that we can now fit the equivalent of 500 million transistors on the head of a pin. They're getting down to the 9 and even 7 nanometer scale. This is incredible. This is what allowed Moore's law to occur. And you know, the devices we have in our phones, everyone has a 12 megapixel device. When I was a student beginning my graduate studies, a 500 by 500 pixel device, so 250,000 pixels, cost something like $500,000. Yeah, and now everyone has 12, 20 megapixel cameras. So that's all quantum physics. Another example is Einstein's general theory of relativity. This crazy sounding theory that the presence of matter or energy warps the shape of space and the passage of time in its vicinity. And the warping actually occurs spatially into a dimension that we can't see. But if we were to slice it with a plane in any direction, you would see that it's warped in this additional dimension. Here I show you just a two-dimensional example. If you have a flat space, a Euclidean space, into which you put a bowling ball, and then you flick a little ball along that surface, it'll follow a curved path. The moon orbits Earth because it's moving along its natural path in a curved space. Newton's formulation of gravity was just an approximation. It's a very good approximation that works for rockets and cannonballs and ballistic missiles and things like that. But this, we think, is a more complete explanation of how gravity works. And even this is incomplete because it doesn't not include quantum physics. So you might say, well, even if this is true, of what value is it? Is it just an intellectually stimulating exercise for a theoretical physicist? No, it's not just that. In fact, if you look at today's, where'd it go? There we go. GPS based on physicists and engineers' understanding of general relativity. Because it turns out there are a bunch of satellites orbiting Earth in 12-hour orbits. And they send out radio signals with a timestamp. And then those signals are received by your device in your automobile, also with a timestamp. The difference in time multiplied by the speed of light gives you the distance to the satellite. If you know the distance to at least 4 satellites at the same time, you uniquely determine your location on Earth. But it turns out that the clocks on the satellites run at a faster rate than the clocks down here on Earth, because they're in a weaker gravitational field. And if this effect, purely of general relativity, had not been taken into account by the physicists and engineers who designed GPS, GPS would not work with all of its military and commercial applications. So there you go, an example of general relativity for which Einstein, a century ago, had not the slightest practical application. He just wanted to understand how gravity works. Why does the moon orbit Earth? Why does Earth orbit the sun? So you never know what practical spin-offs there might be. So, breakthroughs of this sort often require outside-the-box thinking, a fundamental, creative new way of looking at a question and trying to solve it. When Einstein tried to understand how Newtonian gravity works, he couldn't just apply a Band-Aid, he couldn't just fix a cut. He had to come up with a scheme by which gravity works, and this bending of space and time was the model he came up with, but an extreme example of outside-the-box thinking. So what I'd like to show you today is that the process we use in science to solve complex problems actually has broad applications and is a model for strategic thinking and execution for business, technology, and entrepreneurs. And I have a reasonably young audience here, although, as Lana said, it's great that the older generation is coming back and learning these new techniques. But this is a pretty young audience, and you'll move on into many interesting fields in your lives. And I hope that you'll be able to apply some of what I tell you today that's based on my perspective as a scientist, but is broadly applicable in many other walks of life. And what I'll be discussing with you today is not just the expansion of the universe, but the accelerating expansion of the universe, a very surprising result that our teams came up with in 1998 and then were recognized with the 2011 Nobel Prize in Physics. This is an insight that was of fundamental importance. As you will see, it changed our view of the universe, of what we thought the composition of the overall universe is. It required extensive innovation, outside-the-box thinking, big data, large teams, fierce competition, and international cooperation as well. And all of these things are attributes of life in many other different walks. So let me, I guess it didn't, Kind of strange. Yeah, there it is. Well, that's what I said, but there it is in Russian for you. So let's start with Edwin Hubble, who in 1929 discovered the expansion of the universe. He looked at these giant collections of stars, galaxies, and he noticed that they're moving away, and the ones that are farther from us are moving faster than the ones that are nearby. So this one is moving away from us, but these ones which are farther away are moving faster. Now, the view from the Milky Way Galaxy looks something like this. We're right up there, and all these other galaxies are moving away from us. Do I have a laser here? Yeah, I have a very weak laser here, but that's okay. You can see that the more distant galaxies are moving faster than the nearby galaxies. This, in and of itself, is not evidence for an accelerating expansion. Rather, this is evidence for a uniform expansion of the universe. But before I move on, let me pause, because there's something rather peculiar about this diagram. What looks strange to you about this diagram? Anyone? Yeah, we're at the center. Several of you said it. Why should we be at the center? Do all these other galaxies not like us? Is it something we said that upset them? Do we smell? Or are all these other galaxies lactose intolerant? Do you understand the joke? We are the Milky Way Galaxy, so lactose intolerant galaxies. Or when I teach my students at Berkeley about this concept, I joke with my students, what is the problem? Are we from Stanford or something like that? You know, Berkeley, Stanford, big academic and athletic rivalry. No, we don't think we're in any central location. Rather, this is what you would see no matter which galaxy you happen to live in if you have a uniformly expanding universe. And here I give you as an example a hypothetical one-dimensional universe where the space itself is expanding and the galaxies are represented by these little table tennis balls. I saw your game room right over there, ping pong balls. So no matter which galaxy you're in, you would see all the others moving away. So you would think that you're at the center, but you're not at the unique center. And moreover, you can see that the more space there is between two galaxies, the faster will be the expansion, because every little bit of space expands, say, in 1 second. So the more space there was between two galaxies, the faster will be the speed with which they move away from each other. Now, if you don't like a one-dimensional universe, you can have an expanding loaf of raisin bread where the dough is uniformly filled with yeast, and you let it sit there for an hour, and let's say the distance is double. You can see that from the perspective of any raisin, all the others are moving away. And this holds either for an infinite universe or one that wraps around. And since every bit of dough has yeast in it, raisins that are initially farther apart from each other move away from each other faster than the ones that are close by. So, we're not in any central location. But the universe is expanding, and with today's great telescopes, the Hubble telescope and others, we've measured the speed with which the universe is expanding. But we expect the speed to be changing with time. And this goes back to this concept of Newton. He saw the apple fall from the tree. And he reasoned that all objects pull on all other objects through this invisible force, the force of gravity. Indeed, he realized that the moon is orbiting Earth for the same reason that apples fall. The moon is falling toward Earth, but it also has a perpendicular speed, and so that ends up being an orbit. So he united terrestrial phenomena with celestial phenomena. It was a magnificent achievement. But Newton had no idea how gravity actually works. He said that he doesn't know how it works, it just works. Well, all of the galaxies should be pulling on each other as well. So, just like Earth pulls on the apple, the universe's expansion should be slowing down. And if the density of the universe is high, if there's a lot of material everywhere, then the expansion will slow down so much that it will someday stop and reverse its motion, and the universe will collapse in on itself. So if you were living in such a universe, and you're watching the galaxies, and they become fainter and smaller with time, and you think you live in a well-behaved universe, and then you notice something peculiar, and right around now you get a little bit nervous, and then the universe collapses in on you. So that's it for you. Well, too bad. But there's another possibility. The density of the universe might not be very high. In that case, the expansion slows down, but does not come to a stop. So that's a little bit like throwing the apple so fast that it escapes from Earth, a speed of 11 kilometers per second or greater. Gravity slows it down, but never brings it back. Okay, so that's what rockets do. So in that case, the universe would expand forever. The galaxies would keep on getting smaller and fainter with time. Instead of becoming dense and hot and ending with a collapse, the universe would grow forever bigger, darker, colder, a very different fate from the collapse. And we would like to know which kind of universe we live in. Will it recollapse or will it expand forever? We just want to know. It's pure curiosity-driven research. Maybe someday it will have a practical application, but I don't care. I just want to know. And maybe kids will be excited by the discovery. So how do we do it? Well, again, let's come back to the proverbial Newtonian apple. If you measure how fast it's moving at different times, you can predict whether it will reverse its motion or not. If it's been slowing down a lot, then it will someday stop and come back. If it hasn't been slowing down very much, then it'll keep on expanding forever. So that's the idea. And that idea is the big picture. You come up with an overall goal, a question that you want to solve, a new product that you want to make. Think great thoughts. Be ambitious. Focus initially on the big picture. The details are crucial, of course, but you can deal with them later. First, formulate the big picture and keep your goal, your focus set on that. Don't drown in the details. You can deal with them later. And don't be afraid to fail. It's okay to fail. In Silicon Valley, there's a new mantra: fail often, fail fast. Because if you're not failing, then you're not thinking of sufficiently ambitious new ideas. You're stuck in a rut. Okay? Well, then you can deal with the details. And so, how do we measure the past history of the expansion? We live today. We can measure the current rate of expansion. But how do we look back into the past? You look back into the past by looking far away. Light does not travel infinitely fast. It takes a little over 8 minutes for light from the sun to reach us, because the sun is 150 million kilometers away. Even the typical nearest stars are tens or hundreds, maybe 1,000 or 2,000 light years away. So you're seeing them as they were tens or hundreds or thousands of years ago. If you look at galaxies that are perhaps 1 billion light years away, 1,000 million light years away, or 4,000 million light years away, or 9,000 million light years away, you're seeing them as they were 1, 4, 9,000 million years ago, not as they are now. And encoded in the light that you get is information about how much the universe has stretched, has expanded during the time that the light was coming toward us. So we need to determine the distances and hence the look back times, how far back we're looking at these of these galaxies. Well, how do we do that? For a nearby galaxy, it's relatively easy. You choose a star, let's call it Lara, just for fun. And you study that star, and you realize that it's just like the upper left shoulder of the great hunter Orion, a stupendous, magnificent, brilliant star. It's called a red supergiant. And it's sufficiently nearby that we can measure its distance. I can't tell you why now because it would lead me too far astray. But you determine that Lara is exactly the same type of star. And you look at how bright that star looks. And then you can determine how far away it is. You do this all the time when you judge the distance of an oncoming car. You've looked at the headlights of a car that's nearby, perhaps 2 meters away, okay? And then you look at cars whose headlights are fainter. And your brain almost automatically makes this calculation of how far away the car is. If you're not very good at doing this, you shouldn't be driving at night, okay? But you're using what's called the inverse square law of light. Well, cars, stars, it's the same idea. Find a star in a galaxy whose properties you know, measure how bright it appears to be, and that tells you how far away the galaxy is. Seems simple enough. But of course, for galaxies that are thousands of millions of light years away, and by the way, a light year is the distance light travels in a year. It's very large. 10 million kilometers is the distance light travels in a year. And we're talking about galaxies that are thousands of millions of these light years away. You can't see individual stars. They're all too faint. They merge together. So we were told that, you'll never solve this problem. Give up. Forget it. It cannot be done. Because you cannot see individual stars in galaxies that are sufficiently distant to allow you to measure the expansion history of the universe. The stars technique only works for the big nearby galaxies, an example of which I showed you a few minutes ago. So, our answer was no. Innovate. Let's see if there's a way of doing it that doesn't involve normal stars like our sun. And indeed, by thinking this way out of the box, we came up with a solution. In fact, it was a solution that astronomers had considered decades ago. But at that time, they did not have the technology and the computers and the detectors with which to pursue this particular technique. But the technique was already known. And it involves exploding stars. Now, our sun will not do this, but some stars literally explode at the end of their lives in a titanic act of self-destruction. They become millions or even thousands of millions of times more powerful than our sun. And indeed, It is these stars that cook up through nuclear reactions heavy elements like the carbon in your cells, the oxygen that you breathe, the calcium in your bones, the iron in your red blood cells. They all came from stars like this that then exploded. And 4.5 billion years ago, our solar system formed from these elements. So as Carl Sagan used to say, we are made of stardust. Each of you is made out of the elements, cooked up and ejected by stars like this. Kind of a very powerful thought. But these things are very, very bright. Here is one star that exploded in a galaxy of 1,000 million stars. So these things are so powerful that they can be seen thousands of millions of light years away. It's an exploding star, a supernova. Supernova is what they're called. Now, if our own sun were to do this, then sunblock of 50 would not protect you. You would need sunblock or supernova block of a few thousand million. But don't worry, be happy. Our sun is not going to do this. If it does, the University of California at Berkeley can fire me. But I won't care at that point. And frankly, I think they'll have bigger problems on their hands than an astrophysicist who assured them that the sun would not explode. Okay, well, if we find such objects in galaxies whose distances we already measured using reasonably normal stars, like that one right there, call it Lara, and this one here, Christina, who is my connection to Sberbank. If we've already measured the distance of this nearby galaxy, and then a supernova goes off and we measure how bright it becomes, well, then we can calibrate how powerful it really is. That's like the car that's 2 meters away. You know the distance of the car and you look at how bright the headlights are. That tells you how powerful they really are. And then you go and find more distant examples of these supernovas. But first you have to find the nearby ones. So the way my team does it in Berkeley is by using a relatively small telescope, by today's standards, only 3/4 of a meter in diameter. But it's been programmed to take photographs of thousands of galaxies. And it repeats the process. It takes pictures of the same galaxies, and usually there's nothing new. But sometimes there is something new. You can see the arrow there. Well, the arrow we put in with Photoshop or something. But you see that it's pointing at that object that was not there in the previous picture. So that's a supernova candidate. It could be an exploding star. There are other things it could be as well. But out of maybe 1,000 pictures in a given night, there might be 10 or 20 candidates of this sort, supernova candidates. And then I have students, undergraduate students, who use their superior eye-brain combination to examine these candidates and determine which ones are likely to be genuine exploding stars, worthy of further investigation by our team. And these students gain real research experience at an early age. They learn how to code, something you all appreciate very much. They learn how to do data analysis, statistical error bars, systematic errors, and the thrill of participating in a discovery. Few of these students will become professional astrophysicists, and that's okay. But they'll go on to become members of Google or Microsoft or Facebook or something like this, where the skills they learned and the research experience that they were given the opportunity to pursue as undergraduates, it will help them in their work. So, what can you conclude from this? Build and nurture a first-rate team. get a diverse set of people, preferably from many different backgrounds, explain the importance of the overall project to them, a project that might be very difficult to complete. But if you clearly state each of the person's particular goals and responsibilities and roles, and if you make each of them understand that they are a critical component to the success of the overall project, this will motivate them to work hard and to contribute to the overall project, especially if you provide positions that can develop into real leadership positions. You know, a big, giant project may well have many smaller units that can be led by individuals. This provides great experience for them, and of course then give recognition and incentives. This morning we had the Sparbanks Awards celebration, which was really very impressive. Something like 150 awards out of, 300,000 employees. So these were quite special people. But this is the kind of thing where a major project that requires many, many different components, you might wonder, how do you motivate people? This is how you can do it and achieve the goals of the overall project. Okay, so now, going back to the supernova, we find a bunch of them in nearby galaxies like this. Then, we want to find more distant ones in galaxies that are thousands of millions of light years away. And here's a supernova that went off, and the light eventually reaches our galaxy. But it has been stretched by the expansion of the universe. Let me show that again. Oops. Let me do that. Sometimes it works, sometimes it doesn't. By measuring the stretching, the so-called redshift, you can tell how much space is expanded. And by measuring the apparent brightness of the supernova and knowing how powerful it really is, you get the distance, and hence how far back in time you're looking. This is like judging the distance of a distant car. So this is what we need to measure. This is what we need to do. And it's hard because these exploding stars will be in very, very distant galaxies. They will be very difficult to find. People said that, okay, even though we figured out a way to do this, we won't be able to actually achieve it in practice because these supernovas are so far away. Well, our response was to accept new challenges, to have the courage to pursue lofty goals under difficult circumstances. Again, don't be afraid to fail. We could have failed in this project, but at least we tried. And in this case, we didn't fail. Think strategically and creatively to overcome the obstacles that are thrown at you. Look for clever solutions. How did we do it? We used big telescopes with large cameras attached to them, a little bit like the cameras you have, digital cameras. And these cameras can take pictures of wide areas of the sky. Each of these fuzzy little blobs is like the Milky Way Galaxy. There are thousands of them. And if you take pictures like this, separated by several weeks, then you can find faint little points of light that appear in some of these galaxies. Those are the exploding stars. Well, this now is the era of big data. These pictures are many millions of pixels. And we could not do this kind of work decades ago. because the detectors did not exist and the computers with which to analyze the data did not exist. But now in the big data era, we have these expensive telescopes, satellites, computers, and we can have large international collaborations that have access to the different types of equipment that we need. So we can find the distant supernovas. I'll show you a small subset of one of those images. These are data upon which we based our discovery. A picture taken on the 7th of April, 1997. Another picture 3 weeks later. Subtract the one on the right from the one on the left. Again, you can do this now digitally for thousands of millions of pixels. There's some noise. That's okay. Any measurement process necessarily has some noise associated with it. But here, cleverly placed in the center of the square, is something that looks like it could be a supernova. And a Hubble Space Telescope picture of it a few weeks later, this is in May, reveals it as well. And it's marked with an arrow, so you know it's got to be right. Well, we don't know for sure until we study it in detail. And that is what my role was on both of the teams that made this discovery. I have access to the world's greatest telescopes, the 10-meter Keck telescopes in Hawaii. And I'm trained to spread the light out into a spectrum and to analyze the light. And I've been studying exploding stars since 1985. So it was my job to examine the candidate supernovas that my colleagues found. But you know what? For a long time, no one wanted to give me the opportunity to use these telescopes to examine these faint little blobs that I showed you before. Because other astrophysicists were convinced that we would not be able to find them. So they said, Alex, why should we give you time on the world's greatest telescope when you won't have anything to observe? It would be a waste of time. We had not yet convinced them that we could find these objects and take additional measurements with which to analyze them. So what I did was, I used some of the time that had been allocated to me for other projects, more mundane projects. And they gave me telescope time. So I said, well, you know, I'm going to use some of my time to examine these faint little things that my colleagues found. Oops, what's going on here? Am I going, no, oh, I've already shown that. Somehow it went backward. I'm not sure why. Okay. Yeah, that's really very strange, but that's okay. Maybe I was just kind of pushing on the button all the time. Come on. Yeah, that's very strange. Okay, it went back many slides. All right, so I was able to use this telescope to show that the work could be done. And then the committees that would assign time on these giant telescopes said, yes, what a great project. Here's a whole bunch of time with which to do this project. But remember, earlier, they didn't want to give the time. So my lesson here was that we thought outside the box. We found a way to conduct the project with the resources that we already had. We took a promising risk. For some reason, my computer is showing something strange. Achieve the first steps of your goals with the resources already available. You may not have all the resources you need to achieve your goals, but once you demonstrate a proof of concept with the resources you already have available, then new resources might be coming your way. It's a little bit like securing the first bit of venture capital and then being able to demonstrate that you actually know what you're doing. So, So convert skeptics into supporters of your project. All right? So, here you see 3 of these very faint supernovas, which I was able to show were supernovas with the Keck telescopes. And the punchline is that they're faint. They're very, very faint. In fact, they're so faint that the derived distances are bigger than expected. What do you mean, bigger than expected? Well, let me show you this apple again. Let's suppose the universe is only 1 second old, and I measure the distance of the apple from my hand after 1 second. It's some distance. Let's call it 1 meter. But it's been slowing down. Now, if Earth's mass were less, gravity would slow it down less, and it would go a greater distance in 1 second. I can't make Earth's mass less, but I can do the equivalent. I can throw it faster. Okay, so it goes a greater distance. If Earth were not present at all, and you forget about the sun, many of you said you studied physics, would the apple have any reason to slow down if there's no gravity acting upon it? No, right? That's Newton's first law. Unless there are forces acting upon something, it will not change speed or direction. So in 1 second, it would get to an even greater distance. But that's the best you can do. The apple can't be any farther away than the distance it reached at a constant speed, right? At least in a normal, well-behaved universe where gravity is attractive. The apple can't get any farther away. If you find that it's farther away, then what must have happened? It must have accelerated. It's as though you have a rocket attached to this thing, and it goes zoop, like that. It gets to a greater distance. Acceleration. That's crazy, right? That's absolutely crazy. Okay, there's the apple analogy. All right? Acceleration. How can that possibly be? It seems absolutely crazy. And indeed, we were told that our result is impossible, incorrect. Gravity is always attractive. So you must have done your measurements incorrectly or misinterpreted the data. But no, defy convention. If you've made your measurements carefully and you've done a thorough interpretation of all the different possibilities, and you're led to this conclusion, then, try. Think outside the box. Maybe there's some other explanation for your conclusion. Yes, gravity is always attractive. But what if there's such a thing as anti-gravity, right? Here on Earth, we only see gravity. In our solar system, only attractive gravity. But what if there is something that pushes instead of pulling? It's at least an idea worth exploring, isn't it? It may sound crazy, but it's worth exploring. Think outside the box. Why not? The biggest breakthroughs, as I said in the beginning, often require this. I'm not saying that you should be sloppy. You should be very careful in your measurements and in your interpretations. You should consider all the possibilities. But eventually, if you have checked and rechecked your work, and it appears as though a crazy sounding conclusion is the only thing that is reasonable, then be bold. Make a big splash. Announce your result. The worst that can possibly happen is that you're wrong. that's okay. Unless you're wrong for a stupid reason, like in your computer program, 2 + 2 = 5, that's not acceptable. But if you're wrong for some subtle reason, that in the universe there's some effect that you didn't take into account, but you couldn't have known about it, that's okay. That's the life of a scientist, and it can also be the life of an entrepreneur. Most startup companies fail, but if you don't try, none of the things that you will create will succeed because you didn't try anything, right? The best you can do is do your best, and if you succeed, wonderful, and if you fail, that's okay. All right, well, we were fairly convinced by February of 1998 that we were right, and I had the privilege, actually, at a meeting in Los Angeles to first tell the world about these results at a meeting of astrophysicists. And the headline that came out was, "Astronomers See a Cosmic Anti-Gravity Force at Work." And we use this term, anti-gravity, hesitantly because, first of all, it's kind of a crazy sounding thing because gravity should be attractive. And second of all, people ask us, can we collect this stuff, whatever it is, and attach it to our cars and levitate over Moscow traffic jams, or Los Angeles, or San Francisco, or New York, or something? And the answer is no, we probably cannot collect this stuff. But nevertheless, it's an anti-gravitating effect. And one of the people on Brian Schmidt's team, and Brian Schmidt has a quote there, was a young postdoctoral scholar named Adam Rees, who came to Berkeley to work with me after completing his doctorate at Harvard. And he was given the opportunity to make the measurements on the data that the rest of us had taken. So he was relatively junior. But he made the measurements very carefully, and he very carefully interpreted the results. And as a result, at least on Schmidt's team, he was the first to realize what the data were trying to tell us. And he's now a Nobel laureate. But the point here is, be alert, okay? Opportunities might come your way, and you should capitalize on them. He, as a youngster, took advantage of this amazing opportunity that had been given to him to analyze the data. And he was the one who first made the discovery. Often the official team leaders are very busy running the team. You know, they're doing important stuff, but often they are not the ones who are in the weeds, so to speak, dealing with the details of the data analysis or the actual implementation of the plan. But that provides opportunities for youngsters to step in and make a gigantic splash, right? As Adam Rees did. The other thing is to embrace competition. Here, the two team leaders, Brian Schmidt and Saul Perlmutter, we were not always fighting with each other. This was a staged photograph. Embrace competition for at least 3 reasons. First of all, if you'll pardon the pun, it accelerates progress in the field. Both teams want to be first, or if there's more than 2, all 3 teams want to be first, so they work harder. It accelerates progress in the field. Secondly, it improves the overall quality because both of the teams, or all 3 teams, want to be best. If one team is working in a more sloppy way or not taking into account subtleties that might be affecting their work, then they won't be taken as seriously. So this improves quality. And then finally, at least in science, and I think in other aspects of entrepreneurship and business, the agreement in the results increases your credibility. If someone else got the same answer, then that, makes it more likely that you're correct. And in our case, the result was so unexpected, so outlandish, that had there been only one team that announced it, I don't think we would have been taken very seriously. But there were two teams that announced it. And so other astrophysicists had to take the result quite seriously. And they tested it. And by the end of the year, 1998, no one had found anything obviously wrong with what we had done. Maybe there were subtle errors, but, the better part of a year had gone by, and no one had discovered anything that was obviously wrong. So the editors of Science magazine proclaimed the accelerating universe to be the breakthrough of the year, the most important discovery in all sciences. And the caricature of Einstein looks surprised here because he's blowing multiple universes out of his pipe. Now, you might not have known that there are multiple universes or that they come from the pipes of theoretical physicists. I'm just joking here. There might be multiple universes, but we don't think they come from the pipes of theoretical physicists. He's surprised because this universe is expanding more quickly with time, not more slowly with time as would have been anticipated. And he's surprised for a second reason as well. There's a sheaf of papers here where he has an equation that predicts that nature might well have an anti-gravitating property as well as a normal, attractive, gravitating property. So he actually predicted the possibility that there might be anti-gravity. And it comes in a number of forms, all of which we collectively call dark energy. This is a type of energy that we cannot see, so it's dark. We do not yet understand it, so it's dark from that perspective as well. It's still beyond our understanding. And yet it appears to be present because it's causing this observed acceleration of the universe. And Einstein would have been quite interested in the current results. In 1917, he proposed this kind of anti-gravity effect. But then later, 12 years later, he renounced the idea as having been the biggest blunder of his career. He didn't like the idea after 12 years. Imagine if he were alive right now. He wouldn't be sad like this. Instead, he would be happy and surprised, and a little bit like on the cover of Science magazine there. I think he would be tremendously interested in what we've learned now. Well, many measurements up to now have given us a greater understanding, at least of how much dark energy there is. We don't yet understand what it is, but we know how much there is. And when you average over the vastness of the universe, you find that the dark energy actually dominates. It is 70% of all that there is. Not in this room, not at School 21, not in Moscow, not in our solar system, not in our Milky Way Galaxy. No, no, no. In those objects, regular gravitationally attractive matter dominates. But when you go out over tens of millions of light years and beyond, in the vast regions of what we thought was empty space, it's not empty. It all has the dark energy. And so when you average over very large volumes, it is this dark energy that dominates all that there is. And we don't know what it is. Maybe you, one of you, will figure it out someday. By the way, 25% is not dark energy, but rather dark matter, темная материя, не темная энергия, но темная материя. And we don't know what that is too. But the evidence for that is the subject for a different talk. 5% of the universe consists of the material of which we are made. And indeed, we are only a small fraction of the 5%. So this is not your mother's universe. When I was a student, the only part we knew about was the 5%. Wow, we've come a long way. Well, what is the dark energy? We don't know. We're doing various observations to try to figure it out, to set observational constraints on what it might be, including techniques such as using radio telescopes to look at the universe when it was just an infant. Here we're looking very, very far away, very far back in time to a time when the universe was only 380,000 years old. And I can't get into the technical details now, plus I want some time for question and answer. But the point is, we are using many techniques now, including studying the formation of the large-scale structure of the universe through computer models like this one. These are all galaxies and clusters of galaxies being formed under the influence of both attractive matter and repulsive dark energy. And you can compare these simulations with what the universe looks like right now. Here is what's called the Millennium simulation. This is a simulation of what our universe looks like based on real data. And again, these various techniques give us different ways in which to study the dark energy. And we're slowly coming to a greater understanding of what it is, but we still don't know what it is. The point here is that these modern studies are far too big for any individual or even a big team to address. These are now big, big projects that require much more international collaboration. So the message is that at some point, you need to know when to collaborate. Come on. The simulation does not want to stop. You see, it's so beautiful. Let's see if I can get it to go. Oh, there it is. Yeah. At some point, you need to recognize when to collaborate. A particular project becomes too large for a single team. And although I stressed competition initially, some projects are just too big for one team. Don't compete. Instead, consolidate resources, and the synergy and the cross-fertilization can benefit overall the project. So that's an important message. And that's the stage we're at now in the study of dark energy. We now have teams of hundreds, if not thousands, of astrophysicists trying to study what this dark energy is. It's a little bit like the Large Hadron Collider, a 10 million billion euro project at the corner of Switzerland and France. 80 countries involved, 6,000 to 8,000 physicists and engineers. No single country could have done it, much less a small team or an individual. So sometimes to address the biggest questions, you learn how to collaborate. Well, the physical origin of dark energy is a huge mystery. Many people think that it's the single most important observationally motivated problem in all of physics today. 70% of the contents of the universe. And a possible clue to the desired unification of the two great pillars of modern physics, general relativity, the physics of the very large, and quantum physics, quantum mechanics, the physics of the very small. These are two areas that work well individually, but when you try to bring them together to solve a problem, like the origin of the universe or the middle of a black hole, quantum physics and general relativity are at war with one another. But this dark energy is thought to be a quantum phenomenon that exists everywhere, even in this room. It's just there's very little of it in this room. Okay. So for those reasons, it was honored, the discovery was honored, as I said, with the Nobel Prize in Physics. To the two team leaders, Saul Perlmutter at Berkeley, Brian Schmidt in Australia, and I'm very proud to say that my postdoctoral scholar, whom I mentored at the time that he was just a youngster in Berkeley after having completed his degree at Harvard, he was the third person officially honored. And the rules of the Nobel Prize are that you can't give it to more than 3 people. There was another person on Saul Perlmutter's team, Gerson Goldhaber, who had the result at about the same time as Adam Rees. Perhaps the Nobel Committee waited until one of the 4 people died before giving the prize to anyone. Anyway, it's unfair, but that's the way it goes. But these 3 gentlemen understood that without the rest of us working hard, the discovery would not have been made. And really, the reason we do science is to make the discoveries, not to get prizes and all that. The recognition is nice, but the real joy is in making the discovery. Still, the rest of us were flown out to Stockholm to participate in the Nobel Prize week. And here's Schmidt's team right after the awarding of the prize. Here's Perlmutter's team. I'm not in that picture. That's because the main team with which I was associated was Schmidt's team. And at that time, we were having our celebratory lunch. And at that lunch, my wife, who was going to join me on this trip to Moscow, but then at the last minute couldn't make it, she gave to the rest of us who were not official recipients of the Nobel Prize, she gave us a consolation prize, a t-shirt. Dark energy is the new black, sort of a saying. Do you know that saying? When something is the new black, it's really great. So anyway, some years later, all team members were recognized with what's called the Breakthrough Prize in Fundamental Physics, established by a Russian, Yuri Milner, initially a physicist, who then, I guess, invested in a bunch of things, became a very successful venture capitalist. But he feels that scientists should be treated as rock stars, in part to get more kids interested in science. So he funds this thing called the Breakthrough Prize, and we were all recognized. But again, we do this not for the money or the prizes or the recognition. We pursue science just for the fun of it, to contribute to humankind's understanding of the world. And as a child, I had no real realistic aspiration of ever being associated with a project of this sort. I just wanted to contribute a little bit to humankind's understanding of nature. I followed my passion. I had fun. You're young. Choose something that you love and that you can immerse yourself in. It will become more like a hobby than your job, and you will enjoy doing it. And I felt very, very fortunate as a scientist to be privileged to be working in such an exciting field. So, finally, some parting comments. The road to the discovery of cosmic anti-gravity is a wonderful example of having an innovative idea, thinking outside the box, pursuing it vigorously and creatively, and achieving not only success, but a real breakthrough that influences the world in a revolutionary way. Again, we couldn't have anticipated that this would be the result of our studies. It's a good model for ambitious ventures in the corporate world. It certainly had a lot of examples of passion, enthusiasm, sheer drive, and determination. We all worked very, very hard on this project. Many examples of personal leadership, fierce competition, extensive collaboration, euphoric highs, depressing lows. Things didn't always go the way we wanted. For example, when I was not given telescope time to pursue this work. And finally, for disruptive innovation, it's necessary to be open to new ideas and creative outside-the-box thinking. And so many of you are, learning software engineering that you will later apply to new ideas, creative startup companies, perhaps, creative ideas, the next smartphone, whatever it is that you come up with, set your goals high, think outside the box. Don't let the naysayers slow you down. Innovate. Figure out a way to overcome the problems that others might tell you cannot possibly be overcome. So, спасибо вам.
Друзья, спасибо большое, Алекс, за отличное выступление.
Пожалуйста, спасибо.
Друзья, у нас есть буквально 10 минут на ответ.
Простите, пожалуйста, я слишком долго говорил, да? Простите. Я хотел медленнее говорить, чтобы, знаешь, этот переводчик мог. Да.
Поэтому, друзья, не теряйте время. Вопросы?
My name is Pavel. I would like to ask a question. You said that our universe accelerates with a certain speed, right?
Yes.
And also in your lectures in Berkeley, you said that the speed of light is 300,000 kilometers per second.
Yes.
And cannot be overcome. But if acceleration of the universe is constant, what happens if some parts of the universe goes beyond the 300,000 kilometers per second compared to us? And what happens in time with these objects? Because you said that anything that goes over 300,000 kilometers per second will literally go back in time. Will they go back in time or not?
So here's the answer. Einstein's special theory of relativity says that no object or information can travel through a pre-existing space faster than light. But space itself can and does expand faster than light. Imagine two ping pong balls that are, let's say, 400,000 kilometers from each other. And then every little bit of space expands in the next second by a factor of 2. Imagine that. So suddenly, these two ping pong balls that used to be 400,000 kilometers apart are 800,000 kilometers apart. So they moved apart from one another 400,000 kilometers in 1 second. That's not a violation of relativity. But if you were to send a signal from one of them to the other, that signal would never get to the other one precisely because space is expanding faster than light. So our universe has an observable horizon, a maximum distance to which we can see. It's possibly infinite beyond that. We actually don't know whether our universe is finite or infinite. But Einstein would not be troubled by the expansion of space faster than light. He would have said, no problem, okay? It's because nothing is traveling through the space faster than light.
Alex, my name is Igor Krivenko. Thank you very much.
Also
for
Ukrainian.
Yeah.
Yeah.
Yes.
There you go.
Thank you very much for your marvelous story. It was very
you.
interesting.
Thank you.
My question is for you, as the person who is the most shorthand to all these far objects.
Yes.
What do you think is beyond the edge of the universe?
Well, so the edge of the universe is an interesting question. We think the universe is either infinite, in which case it obviously has no edge, or it wraps around and joins together. So let me give you this analogy. Not a one-dimensional universe, but in this case a two-dimensional universe. Suppose the laws of physics are constrained to operate only on the rubber, technically within the rubber itself. So you can go forwards or backwards, left and right, or any combination of those two motions. But in or out along the radial dimension is not allowed. So in this universe, it's finite. And if you go in one direction, you'll come back to the place from which you started. But it has no edge. You might say, well, what about the radial direction? That's a different dimension. That's not an edge. It's not an edge to the rubber itself. So we think the universe is either infinite or, in 3 dimensions, wraps around a 4th spatial dimension, just as this 2-dimensional curved universe is embedded within and wraps around a 3rd dimension. So there's no edge. Yeah, it's complicated, but yeah. If there were an edge, then it would violate what's called the Cosmological Principle, which says that no part of the universe looks significantly different from any other part. And that's a principle we adopt. It may be wrong, but within our observable horizon, we don't see any difference between the different parts of the universe. There's no obvious edge or special point.
Здравствуйте, Алекс.
Здравствуйте.
Спасибо большое за прекрасную лекцию.
Пожалуйста.
Такой вопрос. Вы, когда говорили о том, как вы измеряете расстояние между
Простите,
галактиками...
опять скажите. Я не понял первую часть.
Вы, когда рассказывали о том, как измеряются расстояния между галактиками, упоминали сверхновые и приводили пример с автомобильными фарами.
Да.
Что фара на 2 метра и на 5 метров ее светимость теряется, мы понимаем расстояние. Но кто сказал, что сверхновые с одинаковой мощностью взрываются?
Это хороший вопрос.
Потому что фары-то могут с разной светимостью светить, и тогда у нас возникнут проблемы в определении расстояния до них.
Okay, so great question. So there are many things that can go wrong. For example, there could be fog in the way. Fog makes a light look dimmer than you would think, and so you overestimate the distance. That's why a number of accidents occur in the fog. People didn't take it into account. So there was a way we could make measurements that would take into account possible fog. What about, as you said, a difference in the actual power of the supernova 5 billion years ago versus now? Well, again, there are ways in which we can test the hypothesis that it looks dimmer, not because of an extra distance, but because it was a less powerful light bulb. I can't go into all the technical details now, but we definitely had to consider those. And yet still, there might be something that is affecting the measurements that we did not think of. That's why it's very important to have many independent techniques that give the same result. That builds confidence that one's result is correct. And many astrophysicists did not believe the result based on supernova for the very reasons you gave, until it was confirmed by completely independent techniques. And I mentioned briefly this technique of looking at the universe when it was very young, and there are other techniques as well. We're still not absolutely sure, because science is different from a mathematical proof. You can always be wrong. What we hope is that with time, we get a progressively more accurate, quantitatively complete and correct description that explains phenomena that we've seen and makes predictions of what the measurements will yield for phenomena that have not yet been observed. And if those predictions are confirmed, we pat ourselves in the back and we say that our theory is more complete, but we're never sure that it's wrong. This is one of the fundamental ways in which science, a process of hypothesis testing, is different from articles of faith, where you just believe something. It's a different way. So far, we've not found anything wrong with our interpretation of the accelerating universe being driven by dark energy. But if someone among you figures out that we missed something very fundamental and we're completely wrong, wonderful. That's how science progresses.
Alex,
Yes.
Pavel Sukhachov, a student of School 21. First of all, thank you for extraordinary speech. It was amazing.
Thank you.
My question is regarding the expansion of universe you've been saying. Do you feel that this expansion in the universe happening inside our planet as well? I mean,
No,
how the things are speeding up, how they're...
Yeah, so the expansion only occurs in relatively empty regions of space. For example, our bodies are held together by electromagnetic forces.
Right.
And so we're like a spring that's so tight that the dark energy is not expanding us. Earth is held together by gravity. It's not expanding. Our solar system is held together by the sun's gravity. It's not expanding. Our Milky Way Galaxy is held together by all the gravity of the stars and the dark matter. It's not expanding. You have to go out to about 10 million light years and beyond, by which point the universe is sufficiently empty and gravity is sufficiently weak that this anti-gravity can take over.
What about the time curving?
Yeah, the time curving, well, that occurs to some degree everywhere, even around Earth.
Right.
You know, the GPS satellites have clocks
Yeah,
that experience slightly different time than the clocks down here. The net effect is 38 microseconds per day of speeding up. That's how much faster the GPS clocks are running than here. So to some degree, you can see these effects nearly anywhere. But the dark energy is so weak that locally gravity is so strong that, again, it's like a spring that you can't stretch at all. Yeah.
Thank you so much for a splendid lecture. You've been talking about thinking outside the box and coming to different conclusions.
Yes.
And as you said correctly, we are coming to a point in our understanding of the universe where there is a mismatch between explanations provided by the Newtonian physics and quantum physics, for example. As you said, we cannot explain precisely what happens inside the black hole, right? Mm-hmm. And as far as I understand, today we have that thing that tries to bring all of those mismatches together as a string theory.
Yeah, string theory, yeah, and superstring theory. Yeah.
Yeah, many strings.
Yeah.
Do you think we will come to a point in our understanding of science where we have to scratch everything that we knew before that, like classic Newtonian physics, and adopt something completely new? Well,
that's right. So often physics advances just by small changes in the theory, but sometimes you have to have a brand new way of looking at things, such as Einstein's view of curved space-time. That's completely non-Newtonian. However, if there had been airplanes flying around back then, it's not that suddenly they would have fallen out of the sky because Newtonian physics is incorrect. Newtonian physics is a fine approximation to what general relativity says when you have small speeds and small masses, okay? General relativity, we think, will end up, and quantum physics, we think, will end up being a fine approximation of string theory in the domains to which we've been applying them up to now. It's the singularity in the black hole, or the birth of the universe, or the energy of the vacuum. That's where we have problems bringing them together. And it may require a completely different view of the universe. But in the limit that you're considering systems that are already well explained by the physics that we know, those new theories will have the same result. You see, they might look completely different. Indeed, as I said, Newton had no mechanism for gravity. He just said F is proportional to the product of the masses and inversely proportional to the square of the distance between them. But he said in his Principia, I have no idea how this works. And what Einstein tried to do is come up with a way. Well, in Einstein's theory, there is no gravitational force. It's all a curvature of space-time, and objects are simply moving along their natural paths in that space-time. But, you know, I went to the museum yesterday, and there were all these, you know, the metal armor that people wore centuries ago, and the swords and other things they used. Those are all based on Newtonian physics. You know, you hit someone with a hammer. That's no different in relativity. You see what I'm trying to say? Yeah, the theory may look completely different, but in the limit of applying it to familiar phenomena, the older theories are just fine.
Hey, Alex.
Yes.
Thanks
Hey.
for this wonderful opportunity. Very inspirational.
Your English is flawless. Even your accent. So you must have grown up somewhere else.
No, I'm grown up here.
Fantastic.
So I have a very simple question.
Okay.
Are we alone in the universe? And
Well-
where are all the aliens?
Yeah, are we alone in the universe, and where are all the aliens? So it's a simple question with a complex answer. Let me just give you a quick version of it so we have time for many questions. And, you know, I'm available for additional time if you're allowing it, but it's up to you. So my own personal feeling on this is that life is probably quite rare. Maybe microbial or bacterial life might be reasonably common, although even that is not at all clear to me. But the evolutionary path to us was so improbable that it probably happens only very, very rarely. I don't think we're absolutely alone, certainly not in our observable universe, within which there's 100,000 million galaxies, 100 milliard galaxies. But we may well be alone in our Milky Way Galaxy, or maybe there's a handful of us. I certainly don't think that there are hundreds of thousands or millions of intelligent civilizations at or above our level, because at that point, at least some of them would have survived and developed technology with which to populate the galaxy. And the fact that we really don't have good evidence for aliens here, you know, you might think otherwise, but most scientists would agree that the evidence for UFOs and all that is really not very good. Area 51 and Roswell and all these things. It doesn't clear the scientific criteria for, you know, that we have come to expect of science. So, you know, it's known as Fermi's paradox. If they're common out there, why haven't we seen them? Well, you know, so maybe they're not common. And so then it's very unlikely that they would have populated the galaxy. We just don't know. I'm all for the search for extraterrestrial intelligence, but I think we're very unlikely, and you know, we haven't seen anyone. The other arguments are that out of the tens of billions of species of life on Earth ever, only humans have reached this level. Moreover, we only reached it a short time ago. Humans 250,000 years ago, early hominids 4 or 5 million years ago. So an intelligent alien looking at Earth for most of Earth's 4.5 billion year existence would have said there's nothing particularly intelligent or mechanically able. And finally, although our intelligence has certainly improved the standard of living of many, if not most people in the past 100 or 200 years, it's also true that our intelligence and mechanical ability has led to our own potential self-destruction. And it's not at all clear that we will get past this bottleneck that we've created for ourselves. And maybe that's something that many or most intelligent aliens have to face and don't actually usually get through. But I guess my point is that intelligence and mechanical ability at our level are not a clear long-term evolutionary advantage. Dinosaurs existed for 160 million years. There's no evidence that they became smarter with time. Cockroaches could survive a nuclear war. Cockroaches have not become smarter with time. A lot of the simplest things are much more able to survive catastrophes than we are. We're a very complex organism. What long-term evolutionary advantage do we have? I'm not sure there is one. So, I don't want to be depressing here. This actually makes our own existence all the more important, right? We might be alone or nearly alone in the universe, in which case we had all better be friends and preserve this planet and improve the relationships between the different countries. Why are we so often at war with one another? Is that important in the long run, when really it's the overall survival of the human race that's at stake? We're technologically a very young society. How likely is it that we'll even be around a few million years from now? I hope we're around, but I'm not at all sure. So.
Алекс.
Oh, gosh. I'm sorry there's not more time for questions. Yeah.
Я хочу от всего сердца поблагодарить
спасибо
за
большое.
выступление. Это было абсолютно потрясающе.
Ой, ну.
На мой взгляд, то, чем занимаемся мы здесь в школе 21, без науки и без физики просто было бы невозможно. Мы занимаемся прикладными вещами. Вы на самом on the edge of the
Ну, я,
science.
наверное, не должен был the first part of my talk where I had to, convince you that pure curiosity-driven research is useful. Probably I didn't need that introduction for this particular audience, but this, I think, was being taped and is being made available for Sberbank overall and their 300,000 employees, and they, being more part of real life, could not unreasonably ask, why should society fund research of this type? Why should they be interested? And so it wasn't just for School 21 that I was delivering this lecture. Yes.
И также я считаю немаловажно, как я говорила, треть наших студентов продолжают учиться в классических университетах. Поверьте, в науке есть сила, в науке есть страсть, и действительно вы можете достичь совершенно потрясающих результатов с помощью того, что вы научились здесь программировать, но все же призываю, не покидайте науку, если у вас есть любовь к этому, потому что вы видите, к чему это может привести.
Спасибо большое. Ой, спасибо.